Our next speaker is Drew Troyer. He is the principal at TA Cook Consultants, and he will be discussing reducing industrial climate impacts by managing parasitic frictional losses and fugitive emissions. You can find out more about him and connect in the speaker profiles.
Greetings, my name is Drew Troyer. I'm a principal with TA Cook Consultants. I'm based in the Woodlands, Texas, which is in the Houston, Texas metro area. Our topic today is reducing industrial climate impacts by managing parasitic frictional losses and fugitive emissions. The pressure is really on industrial organizations to meet what are called ESG goals. And ESG is an acronym for environmental, social, and governance goals. Investors are increasingly demanding that organizations pursue a triple bottom line performance. So in addition to the traditional deliverance of profits to shareholders, shareholders are increasingly expecting us to consider the needs of people, not just our workers, but all of our stakeholders, as well as the planet and the impacts that we have on the environment. Some recent news supporting this is a realignment of the board of directors at ExxonMobil. A small investment company based in New York called Engine Number One put forth 4 names of environmentally active potential board members for inclusion in the ExxonMobil board of directors. 3 of these board members were approved and voted in. They were voted in on the strength of institutional investors such as BlackRock. If you're not familiar with BlackRock, they are the largest institutional investor in the world. They have $7 trillion, that's trillion with a T, in funds under investment. Likewise, in Europe, The Hague passed down a judgment on Royal Dutch Shell requiring that they reduce 47% of their greenhouse gas emissions or impacts by 2030. In big company terms, the time from 2021 to 2030 is tomorrow. I mean, that is a massive undertaking. So what can we do about it? I think proactive asset management can save us money and it can reduce our environmental impacts at the same time. These goals of improving profit and reducing our environmental impact do not have to be in conflict. What we want to focus on today is reducing parasitic energy losses and reducing fugitive emissions. There was an interesting study, or actually a series of studies conducted by the U.S. Department of Energy. And I've amalgamated these into this one chart, but to net this out, using existing, utilizing existing best practices based upon existing technology, the Department of Energy reckons that our petrochemical plants, our refineries, chemical plants, pulp and paper plants, mines, so on and so forth, on average, can reduce our energy consumption by 22%. With some investment in R&D, we can drop that even lower. They also report something I don't consider to be practical, which is the thermodynamic lower limit. But just looking at what we can do with existing technologies today, we can reduce our energy consumption by 22%. Well, in the US, and this is for the industries studied, the other industries which were not studied represent the other half. So these numbers are doubled if you consider all industries. So the DOE only studied, certain industries, but for the industries that they studied, we can reduce our energy consumption by about 3.5 billion megawatt hours. Pardon me, that's our current usage. We can reduce that to 2.7 billion megawatt hours, a savings of 722 million megawatt hours. So if we assume, a 5 cent per kilowatt hour cost, That equates to a value of about $36 billion going straight to the bottom line of companies. It does not pass through the cost of goods sold filter. That money goes straight to the profit line, to the EBIT or EBITDA, whatever profit term you use, goes straight to the bottom line. This equates, and to put this in simple terms, and I've organized everything, I've converted everything to kilowatt hours. So, liquid energy, electrical energy, I've converted it all to kilowatt hours. But this would equate to a reduction of about 511 million metric tons of CO2 going into the atmosphere, assuming a standard $50 social cost of carbon of $50 per metric ton. The impact would be $25.5 billion in terms of reduced social cost of carbon. So we're improving profit by $36 billion, and we're reducing social impacts by $25 billion. It's great when our environmental goals and our profit goals coincide. So how do we do this? Well, as maintenance and reliability professionals, I think we have a tremendous opportunity, and I'm a practicing reliability engineer. I probably have worked with some of you as an advisor. I think that we can do a lot to reduce parasitic frictional losses. One way we can do it is to reduce vibration, by precision fastening, precision alignment of shaft-driven equipment, precision balance of mechanical rotating assemblies, precision alignment and proper tensioning of belts for belt-driven equipment to reduce slip. All of these can significantly reduce parasitic frictional losses. So when you think about normal operation, the lubricant, which separates, and I'm using a rolling element bearing, but the physics are a little bit different, but the forcing functions are the same for sliding contacts, but we get about a 1 to 5 micron film. And under normal operation, that's a low friction film. If we got fairly clean oil, everything works well. However, when we introduce the dynamic forces associated with vibration, what we see is an increase of the load on those surfaces. And if the increased dynamic forces are high enough, they can actually overwhelm the film strength of that lubricant and result in surface-to-surface contact, friction, wear, and energy waste. So we definitely want to manage these sources of vibration. I work a lot in the mining industry. In fact, I'm right now pretty much fully subscribed in the mining industry. We have a lot of belt-driven equipment. And I do a lot of strobe light studies to determine how much belt slip we have. I'm seeing belt slip of 10, 12, 15%. That's just poof energy going into the atmosphere. That's not only waste of energy, but it's also a 10, 12, 15% derate on production. So we get 10, 12, 15% less ore being crushed, 10, 12, 15% less slurry being pumped, so on and so forth. So it's costing us money coming and going if we have these belt slip issues. Additionally, we want to manage parasitic frictional losses by reducing our fluid friction. We start with piping. Man, when I look at industrial pipes, clearly energy management was not a focus. We have undersized pipes, we have too many 90-degree turns, so on and so forth. So, by proper sizing of pipes and, minimizing pipe length where you can, minimizing pipe turns, especially turns that are greater than 30 degrees, optimizing valve selection, selecting materials that are smooth on the inside, smooth internal surfaces can help us reduce parasitic losses due to turbulent friction. Turbulence occurs when our fluid flows relative to viscosity, the velocity versus density, viscosity, and the diameter increase our Reynolds number. So Reynolds number is a dimensionless number, but generally speaking, if the number is below 2,000, we have what's called laminar flow. It's a very efficient flow. That's where the layers, the molecular layers, the fluid, whether it's a liquid, a gas, or a vapor, have different velocities. Maximum velocity in the center, minimum velocity, theoretically zero velocity along the boundaries. Well, when the Reynolds number increases above 2,000, and in particular above 4,000, we enter a flow regime that is turbulent. And with turbulent flow, we have energy being directed in all sorts of different directions. Well, this creates friction, of course, internal fluid friction, which creates churning losses. And those churning losses, that internal fluid friction, manifests itself in the form of heat. So if you don't believe me, restrict a valve that's flowing water or fluid, and look what happens. It's going to get hot pretty quick, right? So that's what's happening. So efficient flow can help us reduce these parasitic frictional losses. Additionally, we need to properly select, apply, and manage lubrication. So we looked at that 5-micron film thickness. Well, vibration creates a dynamic force which can overwhelm that thickness, but we also want to make sure that the lubricant itself is properly selected, it's in good health, it's there in the right quantity, and that it's free of contaminants. Contaminants compromise the lubricant's film strength. Water contamination, for instance, if you have even a little tiny bit of water contamination in your lubricant, it compromises that very fragile element of film strength, one of the elements, that's the pressure-viscosity relationship. Lubricant has a special property whereby when it's under load, and incidentally in those load zones and rolling contacts, the pressures can be very high, 35,000 megapascals or 500,000 pounds per square inch. Well, under those pressures, a lubricant's viscosity increases. I know that we're all familiar with the pressure viscosity temperature relationship. Temperature goes up, viscosity goes down. You may not be as familiar with the pressure viscosity relationship, but the pressure increases the viscosity substantially, and that's a major component of film strength. Water does not possess that physical property, and when it's contaminating our lubricants, it compromises the oil's pressure viscosity relationship. Also, if we have particulate contamination, it bridges those gaps and causes frictional contacts. So all of these things sort of add up, excessive vibration, poor pipe design, poor management of our lubricants. All of these add up to create a lot of parasitic frictional losses. We also have parasitic frictional losses in our electrical systems, and it produces electrical heating. So when we think about energy from an electrical perspective, watts equals volts times amps. Well, amps or current, if the amps are high, that creates electrical heating. So we want to make sure that we're designing our electrical circuits so they're adequately sized, we have good connections, so on and so forth, to minimize that electrical heating. We also want to select high efficiency motors that use less electrical energy to create mechanical motion. Another opportunity for us is where it's appropriate to utilize variable frequency drives, or sometimes called variable speed drives. These motors vary speed by varying the frequency of the electricity that's applied. So we normally see either 60 hertz or 50 hertz electricity. Well, by doing an AC to DC conversion and then doing a subsequent DC to AC inversion, we can alter the frequency. So if I reduce my frequency from 50 hertz to 25 hertz, I cut my speed in half. This gives me a lot of energy saving potential. You do need to consider these conversion and inversion losses in your equations. We want to minimize voltage and current harmonic distortion. So that's reactive power on the line. So if you're on a 50 hertz line frequency, voltage at 100, 150 hertz, these create distortion, which produce electrical heating. Again, a waste of energy. And of course, we want to maintain proper electrical balance in three-phase electric motors. So we have, in an electric motor, we have 3 phases of electric power separated by 120 degrees. These in the rotor of the electric motor, the electricity creates a rotating magnetic field. The rotor, of course, chases that magnetic field. We want the voltage to be balanced. We want the current to be balanced. We want the resistance to be balanced. And we want the inductive efficiency. So that's the efficiency with which the electric motor converts electrical energy into mechanical energy. We want to be balanced across all three phases. If it's not, the byproduct is heat. Again, that's a waste of energy. And of course, we want to routinely monitor and correct our electrical circuit and current conditions, just like we want to monitor our vibration on a regular basis, just like we want to monitor the health of our lubricants on a regular basis. I think another major opportunity for us is in the management of fugitive emissions. So a large amount of energy in a plant is utilized to pressurize liquids or compress gases or to heat water to make steam. And a lot of that energy is lost to fugitive emissions. Whether it's air leaks, it's steam leaks, it's venting steam, we lose a lot of that energy. So we want to make sure that we're managing leaks. Leaks are fairly easy to manage. We can use ultrasonic acoustic emissions to detect these fugitive emissions because they create turbulence around the leak, making them very easy to detect. Very frequently, these occur at fastening joints. So, with a wrench or a spanner, we can often get in and fix that leak as found. So it's not uncommon for a plant to have 20 to 30%, for instance, of the total volume of their compressed air leaks, of the compressed air is leaking. It's just sending energy and money out into the atmosphere. Even worse than that is in natural gas systems, or leakage of volatile organic compounds, we have a fire and explosion risk. There's also health risks associated with breathing this natural gas. And when you think about methane, which is the primary component of natural gas, it is 80 times more powerful than CO2 as a greenhouse gas. Well, to put this in perspective, the natural gas industry loses 3.2% of its total, production. The natural gas industry, the production, the processing, the storage, the transportation, the distribution, 3.2% of the gas is lost. Well, let's think about that from a profit perspective. All of the costs associated with that gas are sunk at the point of leakage. So if we stop the leakage, we increase the amount of sellable gas. So all of the revenue for that gas, which is about $4.50 per 1,000 cubic feet right now in the United States, that money would go straight to the bottom line. Additionally, we're losing the money to energize, to pressurize that natural gas. So we're missing it, all over the place. And these leaks, particularly methane leaks, are fairly easy to spot. This is an image from my friends at Snell Infrared. So this is an infrared image of a massive emission of natural gas, methane, from a valve. So this is very controllable. And in fact, studies have indicated that most of this leakage is super emitters. So rather than having a gazillion little leaks, we've got a smaller number of these super emitters or large leaks of methane, which makes it a lot easier to put these under control. So what's our goal with precision equipment energy management? We want to transition from a current state where the machines are shaky, they're noisy, they're leaky, they're hot, they're dirty. We want to transition to an optimum state where the machines are smooth, quiet, they're tight, not leaky, they're cool, and they're clean. This is our goal. So just some conclusions and next steps. So I'm just telling you, as a guy who works around the world in all kinds of different industries as a reliability engineer, I think, depending upon the industry and depending upon the location and your current practices, I don't think we can get through maintenance and reliability all 22% of the opportunity. However, I think we can probably get 5, 7, 12, some cases 15% by targeting these parasitic energy losses and fugitive emissions. So I think that we have that opportunity. There's huge benefit to us. We have energy savings, goes straight to the bottom line, reduce greenhouse gas emissions, makes us better citizens in the eyes of ESG investors. We reduce our life cycle cost of ownership because, pressurizing fluids and all of the things that we've talked about put strain on the equipment. We also can increase our productive throughput. Then we need to, once we define the opportunity, we need to define, what changes need to be made, what hardware changes, what software changes. Hardest part is the people-aware changes. What are we going to do in terms of practices of people? So I will tell you that, changing the culture to, proactively target these parasitic energy losses and fugitive emissions, that's going to be the hardest part. You're going to want to manage that process very proactively. I want to thank you for your time today. Again, my name is Drew Troyer. I've referenced some documents that you might want to get, or you may want to contact me with questions. If you are interested, you may reach me at d.troyer@tacook.com. Our website is www.tacook.com. I'm also co-founder and editor of the RAM Review. This is a weekly electronic publication. I write a weekly column on various topics of reliability engineering, asset management, and sustainable manufacturing. It's free. You can subscribe for free by visiting www.theramreview. You'll get a weekly newsletter. We call it Dispatches to the Plant, and anything I or any of the other contributors have published in the history of the publication are available and searchable at the website. So thank you for your attention and wish you farewell. Thank you.
Hello.
Hi there.
It is ready for Q&A time. The first question is RAM stands for reliability, availability, and maintainability? Question mark.
That is correct. It does. However, we changed it to maintenance for our publication because we are a practically oriented publication. We do not target design engineers. So maintainability, generally speaking, would be a design engineer's activity. So we made a decision. Reliability certainly is important for plant reliability engineers. Availability certainly important. Maintainability is designed in. So we modified the name to reliability, availability, and maintenance for our publication.
Does anybody else have any questions? We can give you a moment to type everything out. What is one of your biggest obstacles in getting this implemented in more spaces?
Culture. Yeah, it's culture. So, when you look at why machines fail in the plant, 80% of what goes wrong is human factors. So, we still, despite, I've been doing this for 30 years, despite these 30 years, in fact, I can recall in the early 90s when we were implementing for the first time really condition monitoring technologies. I was thinking this stuff makes so much sense. Everyone's going to adopt it and change their practices overnight, and I'm going to have to find a new career. But 30 years later, we still have the same problems that we had in the early 1990s. Not a lot has changed. So some organizations have made some progress. Sometimes they take a step forward, then a step back, and step forward, step back. So it's been difficult to get sustainable improvement. So I see a question. Can we say the reliability team is like an auditor on maintenance and operations team? I would say auditor is not the correct term. When you think about the words maintenance and reliability, they're actually opposite. Maintenance is addressing issues of unreliability, and reliability is about avoiding the need to do maintenance. So I wouldn't say that the reliability team is the auditor for maintenance and operations. I would like to think that as reliability engineers, we're the informers and the educators. I would like to think that I can explain to an operator that if they run their equipment in this particular way, these are going to be the adverse effects. And I would like to be able to say to the maintenance team, if we maintain our equipment in this particular way, these are going to be the effects. Now, those effects could be either positive or negative, right? Depending upon the depending upon the nature. So I would say that we, as reliability engineers, probably aren't the auditors. I would say that we're sort of the statisticians. We're the guys that inform. We're risk managers. We inform operations and maintenance and design teams. By the way, don't forget design teams. We advise design teams on the effects of their decisions. So, for instance, in my presentation, I was talking quite a bit about piping design. And I go through plans and I think, what were they thinking? Well, I know what they were thinking. They were thinking, let's get this piping laid as quickly and as cheaply as possible. Unfortunately, though, it's not laid out in a way that facilitates energy efficiency. So it's cheap up front, but it's expensive across the life cycle. Also, and I didn't really point this out in the presentation, but I'll point it out now. When you have inefficient fluid flow, you also experience an increased rate of erosion and wear and tear actually on the piping systems. So it's not just energy. We also have issues that where the life of the equipment, wear and tear on the equipment is increased when we don't have smooth transfer of power, and that's mechanical pathways for liquids, gas, and vapors. Also electrical pathways for electrical energy. So there's increased wear and tear on the equipment.
You have this follow-up.
But as technical staff, design should be aware of all. Yeah, but they're not. So very few design engineers actually have ever worked in the plant. So in an engineer's lifetime, we come out of school and we tend to go one of several pathways. And design engineers rarely work in the plant, and plant engineers rarely get deeply involved in design. And when I say design, I mean in the core DNA of the equipment. So they just tend to have different functional roles. So in my experience, very few design engineers really do have that practical practical knowledge. The other issue, Kashif, is that the way the reward structures are set up, design engineers generally are the reward structures are focused on getting it fast and getting it cheap, not necessarily looking at the life cycle cost of ownership for the asset. I see something from Sean.
If you could implement one government policy, what would you have implemented?
Gosh, one government policy. I don't know. I'm not a politician.
Do you have anything you could say about that, though?
In terms of the areas where I have expertise, the Department of Energy has identified that we have, reasonably speaking, 22%. We can reduce our energy consumption in the industrial sector by 22%. Now let's put this into big numbers. 35% of our energy consumption, and thus 35% of our greenhouse gas impacts, are in the industrial sector, the industries in which we work. So it's 35%. If we can knock 22% off of that, you can run the math. We reduce our greenhouse gas emissions by about 7.5%. I would like to see the government, if I was in charge, perhaps put in place policies to reward organizations for these implementing initiatives that will improve energy efficiency. But honestly, gosh, if I could go find 7% profit somewhere in an industrial plant, and I don't really have to do anything significantly different other than run my plants better, I think I would go for that just on the profit. But it would be great to see the government incentivize. Now, I'm speaking in terms of the U.S. government, and the U.S. government has not shown a great deal of focus really on climate change, not sustained focus anyway. So it's too political. You know, we go from the Paris Accord under one administration to pulling out under the next administration, to getting back in. You have to have a sustained effort. So
Right. We have time for one more. If a SME plant wants to establish their reliability program, how do they develop it? Is there a framework or action plan that can be shared?
Yeah, I mean, there's a number of different approaches. I personally tend to focus on implementing precision maintenance. The reason being is ultimately that's where we address the root causes of machine failure, and then I work back from there. However, you know, you can do a bottom-up approach, which is sort of what I focus on, and I tend to focus bottom-up, and then I show the value associated with that to senior managers and get them on board that way. You know, I find that it's more difficult to start at the top and try to provide an abstract argument to senior management. I feel that it's much better to provide an empirically supported argument for asset management and reliability based upon real success. So, for instance, I'm working actively in South Africa right now, and as our test case, we took a series of pumps and we implemented some precision maintenance initiatives. So we balanced it, aligned it, we lubricated it right, we fastened it down right with nuts and bolts and good foundations and so on and so forth. And we reduced our vibration from 8 millimeters per second to 2.5 millimeters per second. Well, for a rolling element bearing, if you cut your vibration in half, you increase the life of that bearing by a factor of 8. So that's about a 10 to 12 times life extension on the bearings. Now, of course, you've got impellers and you've got other components, but we did enough of those case studies that we were able to make a compelling argument to senior management, and that got their attention. Now, you can go the other way. You can speak hypothetically, this is what reliability will do for you. And I've tried that one before too. I've been at this for 30 years. So I tried that approach, and I just find that this bottom-up approach works a little bit better.
All right, thank you. I really enjoyed that presentation, and I think it's something everyone should be aware of. So,
well, don't forget to count money or energy as a part of your opportunity for reliability. Thank you very much. I appreciate everybody's participation. Have a great day.
You can connect with Drew on his page and the links that he gave earlier if you have any more questions. Thank you.
Yeah.
Have a nice day.
Thank you.
Bye.
Thank you. Bye-bye.